In the previous set of screencasts, we studied the single source shortest paths algorithms, and now we're going to generalize this to all pairs shortest paths. We'll do this at Pearl and Hermes Atoll. I'll tell you at the beginning of the next screencast why this is an appropriate place to do this. And for now, we'll just note that when we enter the atoll, it's one of the most full of life places I've ever seen. We're greeted by the charismatic megafauna, as the biologists call them, the spinner dolphins and the honu, and the curious monk seals, who when you slowly motor by their sand pit, they come out and check you out. To begin, let's review the definition of shortest paths. We are dealing with weighted graphs where you have a weight function that maps edges to real numbers, and so each edge has a number on it, and the path weight W of P will extend the definition of W, which is defined on edges, to paths, to simply say let's sum up all the weights of each of the edges in the sequence in the path. So there's an edge from V0 to V1, from V1 to V2, and so on. So you just sum them up. And of course the shortest path weight is the minimum across all of these sums up here, the minimum cost path from U to V. And that weight will be designated by delta UV. The shortest path will be, of course, be the path that has this minimum weight. And naturally, the all pairs shortest paths problem is to find the shortest path and its weight for all pairs U and V that are in the set of vertices. Now, all pairs shortest paths has some important applications. An old and rather obvious one is to compute the distances between all cities. So for example, you got city 1, city 2, city 3. You might use the all pairs shortest paths algorithm to fill in, all these distances between all the cities. Of course, these are 0 down the diagonal, to fill in all the other ones. Another application that might not be immediately obvious is to compute something called betweenness centrality. I'll draw a little picture here for this. Suppose we have a graph like this where these vertices represent people, and this is a social network. We've asked people who they know, or might be connections in an organization, and we want to know what people have certain kinds of properties in this social network, what people have certain kinds of power. And so betweenness centrality is a measure of how many shortest paths pass through a person. So let's say the shortest path between y and x is this, and between y and w is this one, and y and z is this one. But in order for y to get over to c, it's going to have to go through k and a here and c. In fact, anybody in this group here to get to c has to go through k, and anybody in this group here to get to any other group has to go through k. So what you do is you find all the shortest paths between all pairs, and you count up for each node how many shortest paths go through that each vertex. And then you will find out, for example, that k has very high betweenness without even having a picture of the graph. Just, this can be a really huge graph, and you just run this and generate some numbers. You can find out just by the betweenness number what person, say in an organization, has control over flow of information in that organization. So that's another interesting application. So how can we compute all pairs shortest paths? Well, this iteration of Ulua gives us an idea. Why not iterate our single source shortest paths algorithms? So let's say we decided to iterate Bellman-Ford. What would that cost us? Well, we know that Bellman-Ford is order of v times e, and we would have to run it, v times for each vertex as a start vertex. So the overall cost would be order of v squared e. Kind of expensive. On a dense graph, e is order of v squared, so this is order of v to the fourth on dense graphs. But it has the advantage that it works with negative weight edges. Another alternative is to iterate Dijkstra. Now remember, Dijkstra's algorithm is big O of e log v, and so if we do that v times for the start vertices, we're going to get big O of v e log v, and so that's of course better because instead of a v squared term we have a v log v term. And with the dense graphs, remember this was potentially v to the fourth if we have a dense graph where the e is order of v squared. Here it's only big O of v cubed log v in a dense graph. And also, Dijkstra's has the advantage that with Fibonacci heaps, you can speed the whole thing up to order of v squared log v plus ve, but we haven't studied Fibonacci heaps. My numbers up here are for the binary min-heap implementation that you're familiar with. But one big problem with iterated Dijkstra is it will not work with graphs with negative weight edges. Well, the brown booby asks, can't we just get rid of those negative weight edges somehow? Let's follow the booby's advice and see how we might remove negative weight edges. For example, here's a graph that Dijkstra's can't run on, and it's got some negative weight edges on it. Why don't we find the most negative weight and just say add 5 to all the edges, and that will scale them all up proportionally. They're adding the same number to all of them, and then you've gotten rid of the negative weights. So let's see how this would work. So here's a simpler graph, and first we'll see why Dijkstra's goes wrong on it, and then we'll see how we're going to fix that. So if you remember how Dijkstra's work, initially we have a queue where all the vertices are on it, and distances are all infinite except for the start vertex, and then we take the closest vertex off the queue. So S will come off the queue. I guess I'll just cross it out, and I'll put it up here at distance 0, and then it uses the edges to update the cost of the neighbors. So X and Z both get updated to 2, and so that of course means the queue is reordered. So now Y is later because it's still infinite. And then on the next pass, the next thing off the queue will be X at a cost of 2. And this is going to update Y's cost to be 2 plus 5 is 7, which is cheaper than infinite, so we change that to 7. The queue is still ordered correctly. So on the next pass, Z comes off at cost of 2. And then finally, Y comes off, and you're done. Well, the problem is that there's a shorter way to get to Z. You can go to Z from 2, 5, negative 10, so you can do it at a cost of negative 3, and we haven't found that here. So let's fix that with this proposed fix. I'm going to take the absolute value of the most negative number here, and I'm going to add it to all the edges to make everything 0 or greater. So here's the fixed graph. We've added 10 to all the edges, so there's no more negative weight edges, and we'll proceed as before. Take S off at cost of 0, update its neighbors. This is now 12, Z is now 12, and Y is still infinite, so let's reorder the queue. There we go. And then take the next one off, which would be X at cost 12. Update neighbor Y now has cost, what's that, 27. Q is still ordered correctly. Now we can take Z off at 12. And finally, we're going to take Y off at 27. Now, at first, this looks okay. We found the shortest path here in this graph, which is 12. But the problem is we wanted to use this graph as a proxy for this other graph. We wanted to find the shortest path here, and it would also be the shortest path up here. And the shortest path up here was actually this one. But that is a cost of 27 here. So something went wrong. What went wrong? Well, we added 30 to this path. Remember, this was negative 10, so there's another 10 there. Whereas we only added 10 to that path. So just adding a constant amount to all the edges penalizes longer paths, longer in terms of number of edges, even though they may be the shorter path in terms of weights. So this naive approach does not work. And perhaps because of this, the first solutions that were developed were more of a dynamic programming approach that we're going to see in the third screencast. But later on, somebody had a bright idea to get around this problem. But we're done with this for today. Let's head back to the mothership and for another moonrise.